So now we will study the time complexity of two different algorithms, and these two algorithms, they're basically rooted in different algorithmic strategies. One is based on incremental iterative reasoning. The other one is based on recursive reasoning, and we will look at these two. So our goal basically is to learn how to sort the elements of a given array. So the two algorithms are basically insertion sort and merge sort. And as I mentioned earlier, I'm not going to explain how these exactly were derived. We're not going to think algorithmic, like we're not going to write down the algorithm. I'm just going to explain the algorithm, give you the instruction of the algorithm, and analyze them, analyze their time complexity, okay? So how does insertion sort works? Basically, our goal is, like as I said, is to sort the elements of an array in an increasing order. So let's assume that at some iteration in the algorithm, okay, some time point, some iteration, we have this first part, the green part of the array sorted out. So we have elements from 1 to j minus 1 all sorted out. Next, what we'll have, we have a second part of the array at some iteration of the algorithm, and this second part is actually not sorted, it's unsorted, okay, from j to n elements. So the basic idea of insertion sort is to look at the next element j, okay, in the unsorted, the first element in the unsorted array, subarray, let's call it, okay, and then move it backward in such a way that we can find, so we're going to move it, compare it with all these elements, and insert it into its right position, which means we insert it in the sorted array in such a way that it remains sorted, okay? So this is the basic idea. And then if we keep looking, so in the next step, in the next iteration, we will have the sorted array comprising elements from 1 to j, okay? And then the rest of the array is still unsorted. So we're going to keep looping and doing this over and over again, moving the j element until it is sorted. So if I explain a little bit more, just I give you an example. So let's say here we have, this is sorted, we have 1, 5, okay, 6, 7, and well, these are simple numbers, okay, 8, 10. And then we have the new j right here. It's equal to what? To 2, right? So then what I will do, we will perform a pairwise comparison. We'll look at, compare 10 and 2, 7. So this still, like, these are bigger numbers. And now we find that actually it's smaller than 2, but it's smaller than 5, but larger than 1. So we can put the 2 right here. This is where we insert it. Okay, so that's what it means. Great, so now this algorithm, the key idea of insertion sort is to keep moving the jth element until it finds its right place in the sorted subarray. Now we have a j sorted elements. Basically, this is a new subarray. It's getting bigger and bigger. So next we will move to elements with index j plus 1 and repeat the process over and over again. So this is why it's iterative, right? So we iteratively solving this step by step, like in a consecutive ordered manner. Right, so let's look at the algorithm. So you guys you have the concept, you can sit down when you're like at home and try to write down an algorithm by yourselves, yes?
Using techniques like creating a change the complexity.
That's what, sorry? Using what?
If I use linked list for creating the array.
Right.
The shifting will...
The data structure, absolutely, like the data structure generally changes, can affect the complexity of algorithms, but for the sake of simplicity, since this is lecture 2, we're going just to assume that we're using a simple array, okay? But different data structures actually have different complexities, okay? So, especially, for example, if you're going to search an element in a binary tree, the complexity is different when you're searching for an element in an array. These will be completely different. Okay, great. So in this example, this is the algorithm you guys can see. So let's try together. I'm going to give you a minute also and try to fill this out together before I give you the solution. Okay, so look at this algorithm. Take a minute to try to identify the while true and while false frequency of each line and each instruction. So just to explain, I remember this is, I previously we had only once. Why we have two here? Because actually we do have two instructions. These are two different tests. And in this line we have three because we have three different assignments in a single line. Okay, so and these actually should be multiplied by this one. Okay, this is a compact way of writing it just to gain some space. Okay, great. So what do you guys think for this j equals I? So this is just one. It does not, like, it's just a single instruction. It's quite straightforward. Now, for the while true, what do we have? So we have two tests, right? So the number of times that this will run will always, like, you can consider this as a for loop, right? So the first index, you guys need to keep in mind the first index. The j starts from, actually, well, we start testing j. J is an index. It starts from the beginning of the array till the end, but it does not start from the first element. It starts actually from j. The first test is for j is equal to what? To 2, right? Because it should be strictly greater than 1. So our j actually will vary between 2 and the end of the array, right? We're going to keep moving it, the element, to compare it with a sorted array, right? In an iterative manner. So basically this index, the min and the max, is 2 to n, right? And then this is actually a simple test, testing whether the element a of j is smaller or equal than the previous element. Okay? Great. Now, how many times I'm going to run this while loop? So it's n, if you guys remember, n minus 2 plus 1, okay? And then plus 1 for the exit test, okay? Why minus 2? Because we're starting from j equal to 2. That's actually when the loop is like starting to run. It's like when j, here I can, well, I put strict, but I can put greater or equal to 2, okay? It's two different ways of writing exactly the same instruction. Now, whether it's false or it's true, so here it's like minus 2 plus 1, so this is n times, right? It's going to run how many times? N times. Like, we're always going to loop over that. But then when it's false, what's going to happen? While true, this how many times will be executed? If we remove the exit test, so the previous one, this one is like n times, right? So these instructions nested under the while loop will be executed how many times, guys? N times. And for this one, while it's true, also n times. Okay, and then there is something. What do you guys know this? So this is, I was just explaining the while loop, but we have something else. What do we have? We have a for loop, right? An outer for loop. So this is our for loop, and our for loop goes from here to there, okay? And it's executed n plus 1, but also all of these instructions nested under the for loop, how many times they will be executed at least? Well, n plus 1 for the exit test, but here it's like n times, okay? So it's almost the same thing. We said like n plus 1, so the order of n, same thing. So let's multiply by n. So we have here, this is our for loop, right? Times n, times n, times n. What do you guys know this? So we have like here the complexity is already in the order of what? Generally, okay? It's in the order of n squared. But what if false? So if we have while is false, actually this instruction, what does it mean? It means that actually, if you have an array where all elements are already sorted, 2, 3, 4, etc., so you're going to keep moving your j, but actually these instructions, this allocation, this changing, this changing of two elements, inserting the new element. This is actually the insertion of the new element. Okay, this is the insertion step. It will not happen. You will not insert anything, right? So sometimes you need to really, guys, sit down and analyze your while loop, right? You need to understand how many times it can run and which cases. So in this case, it will not be running. So all these instructions here, they will be 0, right? So it will not run. And in that case, we'll have something in the order of like n. So just to explain, wrap up. So here we have our n, and then times n minus 1. So this is for the while loop, right? And then here, these two instructions will not be executed. And if we multiply, okay, so if we do the math, so we actually, here we're just multiplying this one by these, okay? And then what we're going to have actually is this, okay? So this is the exact number after adding up all the instructions, and we're having something quadratic and something linear. So what is the worst time complexity and what is the best time complexity? It's quite easy. So we know that insertion sort has 2 time complexities, right? So the worst time complexity is in the order of n squared, that's quadratic. And the best time complexity is actually in the omega, so that's the omega, if you guys remember the right notation. It's linear. And when does this happen? For the while loop, it does not get executed. Actually, when you have an array that's already relatively sorted out, like mostly sorted out, okay? And you guys can try this algorithm on arrays. I highly recommend that for each algorithm we see in class, you try it manually and you code it up using your own favorite, like your favorite programming language, C++ or C or Python, okay? Great, so what do you guys know this? So for this algorithm, we have like mostly an n squared, but we have also linear. The next question is, okay, before we go next, actually this is another pseudocode. So you guys can also look at this. So you can write the same algorithm differently. You can have 2 pseudocodes that run exactly the same instructions. So feel free to code up this version or the other version, and you can actually look at these instructions and look at the best and the worst case and perform time complexity analysis of this algorithm, okay? But it's exactly the same, it's just written slightly differently. Okay, now for insertion sort, we're looking at specifically time complexity. So for the worst, and on average, generally, we don't say that we do not assume that the array is already sorted. So on average, it will be also quadratic. But best, if it's like almost sorted, then it's linear. Now, just to remind you, a general rule. So we saw this before. So for the for loop, we have how many times it will be executed, giving the additional time step for exiting the loop. It's m minus n plus 2 for this case. And actually for the while loops, it depends on the while, on the instructions, the conditions of the while, okay? So for the while loop, if it's just while, it's looping over all elements of an array, it will act exactly as a for loop, okay? But sometimes it might not act as a for loop. So you guys need to understand the instructions, the conditions, whether it's while x, a, and b, or whether a or b, etc. So you need to analyze and run the algorithm to understand how to handle the while loops, okay? Great, so this is, what I was exactly saying. So if it acts as a for loop, then you apply exactly the same rule. Now, how can we possibly do better than O of n squared, like quadratic, in sorting n elements of an array? So this is one solution. Like someone has basically, they came up with a solution, insertion sort algorithm. Their algorithm gave us a complexity that is quadratic in time, which is really quite bad when you have really lots of numbers. Still, it's not exponential, it's not factorial, it's not exploding. But the key question that an engineer, computer scientist should ask, can I do better? Can I improve this? Okay? So a second solution was proposed in the algorithm, in this algorithm, and let's see what this algorithm is doing. So you guys watch and tell me what's doing. Okay, what is it doing? You guys want to watch again?
Simply they are grouping the numbers. Like first of all, they're grouping them.
First, they're not grouping. First, they're taking the array and they're just dividing
them and
into elementary.
Compare each two together.
Okay, yes.
After that, they pick the first one from each group and compare them.
So they're doing pairwise comparison and they're like basically merging while sorting. So in the beginning, they're just, breaking down the array, like basically splitting the array into right and left part, and then they're doing the sorting of the right and the left, and then like they're merging. Okay, so this is the basic idea of this algorithm. And this algorithm, here if you look at what we have, so basically on top we have an unsorted array that we want to sort. So we divide the n-dimensional array into n one-unit arrays, okay, so into n elements. So we're going to divide the left part and the right consecutively, okay, alternatively, okay. And then after dividing, now we're going to start the sorting and the merging process, okay. So we repeatedly sort and merge until all subarrays are merged into the single first array, but now it is what? It is sorted. So this is what this algorithm is doing. So now we're merging, but we are merging and sorting. So for example, we have 38, 27. Now 27 is smaller than 38, so we're like ordering them. And we do the same for next. So we need to merge basically the blue ones. Here 27, 38, 3, 43. So you can see now they're sorted 3, 27, 38, 43, etc. So this is, now we merge again, and then it's like top to down, and we get our algorithm merge sort. So this is, the principle of merge sort algorithm. So insertion sort, basically it uses an incremental approach. So we hypothesize that we have like a sorted array and then an unsorted, and iteratively, okay, try to incrementally sort the unsorted array element by element, one by one, okay? As for merge sort, it is rooted in the principle of what we call divide and conquer, okay? And this is based on the principle of recursion, so I'll explain. It's a recursive approach. So merge and sort uses divide and conquer. What it means, so first we have an array. It has a first element and a last element. So these are like basically we divided them by 2, so we have the array. And then sort recursively each part. Like we sort the left part, like the left part recursively, and we sort the last or second part recursively, okay? So this is the main principle. And after that, after getting 2 sorted parts, we're like just sorting and like doing the merging. So here, what is divide and conquer? This is the basic principle. And actually, you guys can use it not just for sorting elements. This idea, you can use it in many algorithms, actually, because you're dividing up the quantity that you're handling. If you have an n-size problem, and you're dividing it into, like you're halving it into 2 subproblems, then it turns out that division is a powerful tool. It kind of, like brings down your time complexity. So this rule, the division rule, you can use it not just for sorting, but you can embed it in other algorithms. So having an original problem, dividing it into subproblem, and then finding a solution for each subproblem individually, and then you merge the solutions together to find a global solution to the original problem, okay? So this principle is very universal. It doesn't only apply to this course. Now, how does it work? How does this work? So basically, first, we divide the element, the n element sequence into 2 subsequences, left and right, each of size, n by 2, okay? And then the conquering step is basically by recursively, okay, I'll explain later in a bit, by recursively sorting all these 2 subsequences. So we sort them recursively, and after getting these subsequences, recursively sorted, then we do the merging by combining them to get the final sorted sequence, okay? So this is how the algorithm works. Let's look at this demo. So the original sequence, as you can see, that's the original array. It is unsorted. So first thing, we divide it into what? Left subarray and right subarray. So this is the division step. Okay, so let's do it here with the animation. So we divide. Then we divide the left subarray. We keep on dividing and keep on dividing the left part. Okay, so this is the first call. And then after that, because it's recursive, we will see the algorithm. Then after that, we need to start basically doing the merging. So here, merge and sort. So we're merging. So 18 and 2016, these two numbers, we're merging them while sorting them. And we do this for the other part. So you can see that we divide after dividing 18, 26, 32, 6. So we have left-hand part. So we're always dividing into left, right, left, right. And then like once you divide, you need to do some merging and keep on dividing and merging and dividing. So this is, you know, an alternating kind of process. So we do this for the right part right now. And then we do the merging. Okay, so you guys see we have sorted out completely the first sub-array from 18 to 6. And then we move to the second right array. We divide the left part of it, left sub part. Then we will sort it and merge. So we flip the 15 and 43, right? And then we will keep on dividing the right part now of the subarray. So this is another division. And then merging and sorting. And here you can see when we merge, we need to sort, okay, the two sequences. And this is how it exactly works. So guys, once I give you the algorithm, please run it manually on a real array and see how it works line by line, okay? And you will be able to animate it by hand. Okay, so sorting strategy, how does it work? So first we split the array into half arrays. So the array has a length of n divided by 2, left part and right parts. And then we sort the left part and the right parts, and then after sorting, we do the merging. So this is basically the algorithm. Now, why it's called recursive? Okay, so this is the whole algorithm, merge sort. We give it an array A. We give it a low element, a low index, okay, and a high index. And then if the low index is smaller than the high, then we're going to basically run all of those instructions. And the first one is actually just a base test, a base case. So we want to give the right numbers. You don't want to give, low larger than high, okay? So what do we do? First, we find the middle point of the array because we need to split, right? So we take the floor function here, so low plus high. That's, from 1 to n, for example. So I give merge sort of array from element 1 to element n, okay? Then we divide by 2, we find the midpoint of the array. And after that, we have two calls. And what do you notice about these calls? The merge sort. The algorithm is calling itself, right? That's why we call it recursive. So this is a recursion call. And we have two recursive calls here. We have the merge sort for the first mid part of the array. And we have the merge sort for the second mid part. So from low to mid, let's say from 1 to n half, and then we have from n half plus 1 to the end of the array. And what do we have last, guys? Merge, right? So in every single call of merge sort, we need to do three things. Like basically call merge sort on two half arrays and then do the merging. So this is the algorithm. How are we going to analyze this algorithm? Let's look. So just to remind you guys, the floor here, for example, if you have 6 divided by 2 is 3, but if you have, for example, 2.5, it's the lower bound, let's call it, okay? So 2.5 to, it gives you 2. Great, now this is the algorithm. I'm not going to go in detail and explain, but you guys can see this is the merge algorithm. So here we're not looking at the merge sort like the whole algorithm, but we're looking only at the merging step. If we have two subsequences, okay, like these two, right, how are we going to merge them? So this is the merge algorithm of the left and the right part, and let's look at that. So the algorithm has different instructions. So we have a while loop, and we have a test here of a pointer k, right, that's moving. So it's like it becomes larger than the midpoint, then we just do the copying here. Otherwise, we will continue to increment and go next in the copying process. So let's look at this algorithm, how it works in the animation. So basically, we compare two elements, 6 and 1. Let's go back. So